next graph. Here I'm plotting the entropies. Once again on the same axis. So this is the entropy of B versus the energy in A. This is the entropy of A versus the energy in A. They intersected at some point, but that's not important. That doesn't tell you anything because these are different sized objects. The total entropy of the system is just the sum of this graph and this graph. These are logarithmic graphs, so I can take the sum. Taking the sum in the logarithmic domain is taking the product in the multiplicity domain. So I take the sum of this graph and the sum of this graph to find the total entropy of the system. And as you can see, the total entropy of the system is going up, which means delta S plus delta B is still positive, still positive, still positive. At some point, delta S plus delta B becomes 0, which means the slope of this graph must become 0 with respect to the change in energy. And that is the maximum in the entropy. That maximum in the entropy will correspond to about 67 or 66.7%. That's the ratio of the sizes of these objects. Remember, these are identical objects, different size, identical compositions. Okay? So what I've been showing on the blackboard is borne out by the simulation as well. I can change the number of atoms and so on. Then now what I would like to do, I would like to find out the slopes of these graphs. For object A, you can imagine the slope is positive, but it's decreasing. But it always remains positive. So for this object, the slope is decreasing. So there's some slope here. My hand is becoming leveler. It's becoming flatter and flatter. So the slope is decreasing, but it's still positive. It never goes down. For this system B, the slope is flatter here, negative. It's negative because I'm plotting B with respect to A. So it's negative and it's becoming more and more negative. So it's becoming steeper and steeper as the energy in A goes up. Or if the energy in B goes down, does the energy in A go up? So as the energy in B goes down, the slope becomes steeper and steeper. And here this is the overall slope. Overall slope of the overall entropy is positive, becomes 0, and then becomes negative. Now what I could do is that I could plot the slopes. That's what I'm going to do now. Actually, I have already plotted them, I'm just going to bring them out. Now these are the slopes of these graphs. The slopes of the entropies. I just do a numerical calculation of the slope. That's what I'm doing. You always use your mobile phone in the class, excuse me. You do it uninterruptedly. That's fine, the course is already over. So if I plot the slopes of the entropies, let's look at A. Red curve is A. It's positive, but it's becoming flatter, so it's approaching 0. Alright? So this is graph A. It's positive, but it's becoming flatter and flatter. So this is my 0. So this is slowly approaching 0. For object B, the slope. Now what I'm plotting here is the slope of of B versus UB. Okay? So I'm not plotting versus A, I'm plotting the slope of the entropy of B versus B. So this is positive, but the magnitude of the slope is going up. As we know, for object B, the magnitude of the slope is still going up. Because here I plotted the slope of B versus the energy in B. So this slope is, both of these slopes, this slope is going up. Now when energy transfer is taking place, the temperature of B is going down, the temperature of A is going up. So the slope of A is going down, which means that the slope must be somehow inversely proportional to the temperature. Okay? Now if you look at the overall slope, of the overall entropy, it started off positive, then it goes to 0, here it touches 0. The slope of the overall entropy, which is this blue line, it touches 0. This is when the total entropy graph reaches its maximum. The slope is 0, the total entropy graph reaches its maximum, and then it goes down again. So you don't want to go beyond this region. If you start off here, you want to end up here. This is your equilibrium. If you start off here, you want to end up here. This is your equilibrium. So you could have started off with A being hotter and B being colder. So you will start off from this side of the graph and end up here. So this is the equilibrium position when the total entropy, change in entropy, the slope becomes 0. And this is when the slopes of these objects, notice this beautiful thing that you couldn't see in my plots, is when the total entropy has a slope which is 0, these slopes intersect. So the slope of A versus A and the slope of B versus B intersect. And at that point, the total entropy is maximum and the slope of the total entropy is 0. So this point, this nice fiducial point, this point corresponds to equilibrium. And it seems that the slope of the entropies of the objects is somehow related to the temperature, because in equilibrium the two temperatures are the same. So if the slopes are the same, the temperatures are the same, slope must be related to the temperature. Now, is it directly related to the temperature or inversely related to the temperature? I'm going to show that on a blackboard. But before that, let me just change this simulation a little bit and have equal number of atoms in both nanoparticles. So 300 in each. Alright, so here is the plot of entropies. Same number of atoms in each. So these are really identical nanomaterials, nanoparticles, solids. And there is now 50-50 distribution of energy. That's the equilibrium macro state. The entropy is maximized here. These are the slopes of the entropies. Now the slopes of the entropies intersect at 50. And this is when the entropy, total entropy is also 0. Because these are equal sized objects now. And if I were to take the inverse of these slopes, I'm going to show that this is equal to the temperature. The inverse of the slope of the entropy is equal to the temperature. So if numerically I took these slopes and took the inverse of these slopes and I plotted them, this is what I would get. So this is the inverse of the slopes that I showed in the previous graph, and they intersect at 50% partition of energy. Okay? And these are the temperatures. Now how do I know that these are the temperatures? Now this was this out of excitement? Yeah, I'm also surprised. I'm also excited about this. Let me show why this works. The slope of the entropy versus the energy graph must be related to the temperature, but how? In equilibrium, we know that the total entropy plotted with respect to the energy in one of the objects A, this slope is 0. Agreed? This is this graph. I have UA. I have the total entropy of the system, total entropy. So in equilibrium, this slope is 0. Okay, so this is 0. But what is ds? ds is dsa over dua plus dsb over dua. Agreed? S is because SA plus SB. Now DSB, let's look at DSB over DUA. Now this is a strange object. I'm plotting the entropy of B versus the energy in another object. So what if I would like to convert this to DSB over DUB? Can I do that? I use the chain rule of differentiation, which means that I need to multiply this with another derivative, which is DUB DUA. Now what is DUB over DUA? I know that my U, total energy, is UB plus UA. So this total energy is fixed. So if I were to take du over dua, what is this equal? What is du over dua equal to? आप बताओ. हाँ, दोनों में से कोई बता दे. What is the change in the total energy with respect to dua? Total energy is fixed. 0. Shabash. So this is 0. This must equal, so I take the derivative of this side with respect to A as well. So this becomes dUB over dUA. This becomes dUA over dUA, which is 1. Which means that dUB over dUA is equal to -1. So this is -1. So this is minus DSB over DUB. So this means that DSA over DUA equals DSA over DUA. This is minus DSB over DUB. And this is equal to 0. Now this is equal to 0. Then in equilibrium, DSA over DUA must equal DSB over DUB. So in equilibrium, the slopes must be the same. Now in equilibrium, which quantity is the same for the two objects? Which measurable quantity is the same? It's the temperature. So this must be related to the temperature. Now the question is this equal to the temperature? Or is it the inverse of the temperature? We have to answer this question. Okay, it's actually the inverse. How? Let's see how. Now this is a typical entropy versus energy graph. This is the slope here. I am finding out the slope at 2 points. Okay? Yes. Because dUB over dUA plus 1 equals 0. Which means dUB over dUA is equal to -1. So just put that -1, I substitute this for -1. It becomes minus DSB over DUB. समझा नहीं बात आपकी? ये नहीं है ना? क्योंकि when I just take this DSB over DUA, it's equal to DSB minus DSB over DUB. I just put it in here. So I get DSA over DUA minus DSB over DUB equals 0. So take this to the other side, this is what I get. Now look at this graph. This is energy, this is entropy. Now, the reading material that I uploaded by Schroeder has a very nice analogy. That let's take this energy to be money, and let's take this entropy to be happiness. So let's finish this course on a happy note. Now, if you look at this graph, and consider this object to be a human being, a man, a woman. So this person, if the money goes up, the happiness goes up. But as the amount of money goes up, right, you go along on this graph, you get some money, your happiness doesn't increase as much. This is normal behavior person. Here, if the money goes down by a large amount, the happiness goes down only by a small amount. If you're here and you decrease your money, so you go down the graph, the money goes down by a large amount, but your happiness goes down by a small amount because the slope is flatter here. So this region of the graph is like a generous region. So you don't care if you get more money, your happiness doesn't, you're already content. Your happiness doesn't go up much. And if you lose money, you don't care much, you don't become much sadder. Okay? However, in this region, which is the greedy part of the curve, you would like to amass more and more wealth. Become more capitalist, perhaps. So you get more money, and your happiness goes up. So you would like to get any little bit of money that keeps you happier. Okay? Now the slope of this graph is just like temperature. In this region, it's the inverse of temperature. In this region, you would like to have more money so that your happiness goes up. The goal is to maximize the happiness. The entropy has to be maximized. So you would like to be happier. If you're in this region of the graph, you'd like to get more and more money because that's going to make you happier. Okay? Which means you would like to absorb. In this region, you would like to absorb money. Because if you absorb money, you'll be happier. If you absorb a little bit of money, you'll be happier. But if you lost a little bit of money here, you'll become much, much sadder because the slope is larger. Okay? So you'd like to absorb money here. You'd like to absorb energy here. You'd like to take energy. And that is the characteristic of a low temperature object. A low temperature object would like to absorb energy. Because absorbing energy will make the entropy go up by a large amount. And you don't want to lose energy because losing a little bit of energy will make the entropy go down by a large amount as well. So you'd like to maximize the entropy, so you'd like to absorb energy here. So this is the low temperature region. And the slope is larger, the temperature is smaller, which means that the slope is inversely related to, is the inverse of the temperature. In this scenario, you can lose energy. You can lose energy because losing energy doesn't make you much sadder. Which means you can give away. You are in a pleasure to be generous. You can give away your energy, your money. Which means this has to be a hot object. It can lose energy because that is not going to change the entropy much. It's not going to decrease the entropy much. You don't want to decrease the entropy much because that's against the law of thermodynamics, second law of thermodynamics. So this is the hot region and the slope is smaller. So this slope is actually inversely related to the temperature. It's the inverse of the temperature. You can put in any arbitrary proportionality constant if you like, but conventionally in thermodynamics, the 1 over temperature is just the slope of the graph versus the energy. This is our definition of temperature. You can also have stranger objects in the universe. An object which is a miserly object, whose entropy is a convex function. So for this object, what's going to happen is, if you lose your energy by a little bit, the entropy goes down by a large factor. Your happiness drops by a large amount. Stars have this property. The energy of the system goes up, the entropy goes up, but the temperature, look at the slope here. The slope here is flatter and it's becoming more steeper here. So the temperature is actually decreasing. So put more energy into a star, its temperature drops. This is a strange behavior. In other words, stars have negative heat capacities. So you put in more energy into a star, its temperature actually drops because the slope is becoming more steeper here. So there are other kinds of anomalies, other kinds of strange objects in nature. Nature is not unilateral, it's not monotonous. So another kind of object, which is the most content person I've ever seen, is one whose entropy versus energy graph was actually like this. You increase the energy, the entropy goes down. You increase the money the person has, his happiness level goes down. So this is like a dervish. So he doesn't want to have money, just wants to give it away. So there are objects that have entropy graphs of this kind as well. Now don't confuse this with the graph of entropy of B versus A that we plotted over there. It's not the same thing. Here this is entropy of A versus the energy of A. Don't confuse this graph with this graph here, because this is the entropy of B versus the energy of A. Here I am plotting the entropy of A versus the energy of A. So there are objects that have properties of this kind as well. You increase the energy, the entropy goes down. You put spins or magnets inside a strong magnetic field, you increase the energy, all of them tend to line up together. So there is no multiplicity, there's only one quantum state, one microstate that becomes available. So magnets have entropies of this kind. But I would like to leave this course on a question that this entropy is something that is extremely difficult to determine per se. So how would you find out the available microstates? The total number of microstates in a system, in a solid. It's impossible. So you have to determine entropies in an alternative fashion. You determine entropies in your chemistry courses, in chemical thermodynamics. You always determine the changes in entropies. But that is under a special kind of entropy in a special condition, like the Clausius entropy. For example, one formula for determining the entropy for a constant volume system is delta S equals CV natural log of T final over T initial, something of this kind. So this relates the change in entropy to something that is measurable, the heat capacity at constant volume and the final and the initial temperature that you can measure with the thermometer. The key idea is that this entropy is a really important concept, and as you can imagine in this week, we've seen that this concept of entropy and the second law of thermodynamics is subtle. There are nuances to it. It's an important concept that needs to sink in, and it takes time for this concept to sink in. But it's a really important concept. It's a law that drives the universe. It's probably more fundamental than the laws of quantum mechanics or Maxwell's equation, because this is what determines how this universe, what the past of this universe is and what the future of this universe is going to be. Alright, so we're going to have our exam on Sunday. It's going to be an exam which is, I think, I still haven't decided because I haven't made the exam yet, but it's going to be mostly short questions or multiple choice questions. And be there on time, and I wish you best of luck. Thank you very much.